Three, two, one. Hello. Sorry for the super delayed broadcast. My internet was down, so I needed to resolve that. So here we are going to be working with this particular. And let me double check to make sure this music isn't too loud for you guys. It's a little strange. Okay, it should be okay. Um, so yeah, it's been a little bit since we've worked on this particular project. I want to restart and then I want to run all. And we should see this populate here in a second. Right now, this is a line number, and an asterisk means that it is pending. And yeah, looks like we just wrapped up. Cool. So, okay, I have a note here. I want a list of every third file name and then do some sort of algorithm here where I have J, which is file names, and a range of K, every third one maybe, so that I end up with this kind of list that looks like this, where I get all of the concentrations uh, kind of all nestled together. And that's something that I'm very interested in. Because right now, I believe as they are, it's in order of trial 1, trial 2, trial 3, the next concentration, trial 1, trial 2, trial 3. So I want to get some sort of association here. Okay, so before I get into what I think I should be doing, I'm going to go look at what my I do another stream on a different day, and I work with this free, I guess it's a software called Trello. It's sponsored by Atlassian, and they partner with Jira, which is used in software development as an agile tool to uh, manage software development. And I'm using it here to kind of get some stuff figured out. Here I see that there's some new stories. The reason why I can tell that they're new is there's no story points on them. And so that's something that I wanted to get set up here. And there's actually a lot of new stuff in this scrub section. If you missed my live stream on Monday, I have this portfolio projects board that's kind of an overview of all of the projects that I currently have executed anything on. And these white cards are things that have been updated recently, and you can tell like I need to go through and revisit some of these projects and bring them up to date. The reason why that's important is because, you know, whenever you develop an application, you want to make sure that you're using the latest security available so that your applications are not vulnerable. Currently, we're working on this tracking potential solvent interactions, and you can see we've done a couple of things in these lists here. We actually have not done anything in the scrub list. We are still in our import or obtain notebook. And so here, there's some things that I want to do. I want to make sure that I'm importing all my libraries. I want to consider external sources. I want to talk about a potential future structure. Um, Jupyter notebooks are great because they can contain code, but what makes them really great is they can contain text as well in markdown format, and then find information on potential issues. That's something that we're very interested in doing here. So let's go back to our current to-do list. On here, we have this thing called a sprint. Those are the things that are currently in progress. And right now, I have 2 cards remaining. Create treatment plan for overall structure, and then create treatment plan for present data. Now, let's look at this. Create treatment plan for overall structure and create treatment plan for present data. Those are actually under scrub. So I am actually going to remove these both. And I do believe each of those had a couple, they both had 8 story points associated with them, I do believe. Treatment plan, oh, 4. Okay, I moved that one down. create treatment plan. This one had 8. So I need to remove a total of 12 story points here. So I currently have 18 total, and I have spent 14. I have 4 remaining. And here I have this evaluate statistics to summarize present. I'm actually going to remove this, and I'm going to remove this card size here because I want to make sure that that's something that I might be doing in the future, but it is not something that I want to do on this current, what is this, 2023-02-21 sprint. So if you are familiar with Agile, you know what I'm doing, which is kind of like updating my sprint as I'm dedicating work. Here I've crossed everything off, but my story points, I still have 4 remaining. So I know that I've completed everything so far. So I'm just gonna get rid of those 4 to kind of zero everything out. Some things ended up being a lot easier than some other things. And instead, I'm going to go to discuss external data sources. This is data scientists. I want to discuss with researcher scientists potential external data sources so that model performance might be enhanced. This is something that's really important whenever you're working in data science. You want to always consider where something is coming from. The reason why I'm giving this 2 story points, even though I would give it 4 because it requires yourself and an external connection, is I am that external connection. And so my comment here about external data sources, I want to have a really solid list of options readily available. Now, this was a project that discussed solvents. So, because it discussed, let me actually write that out. Because this project discusses solvents, it would be interesting to calculate distance, or not calculate, calculate the number of molecules present in each concentration. And something that I want to include here is concentration should be a feature as well, because currently in the data set it just has time and temperature, so I would like to add concentration as a feature, and that will kind of alleviate what I was just talking about here, where I need to get these all organized. What if I just add a column that has that in it? That'd be great, right? And then I can actually I can put these into one big data frame that's sorted by time, because the only thing that'll be consistent between the data. So basically I want to merge all of these 64 data frames onto time after I get the concentration embedded in it. But something that might also be interesting is getting the number of molecules present. And I think I discussed this on Monday. That might create a collinearity problem, but that's something that we can test for and figure out if that's a certain thing that's happening, because concentration is a representation of the number of molecules present, but it's a representation, it's a ratio. So it might be better to have the total number of molecules present than it is to have just the concentration available. So that's something that would be interesting. Throughout this project, I was talking about, back when I was doing the research, I was talking about, because as the concentration increases, there's more likelihood for a solvent-solute interaction because of kinetic molecular theory. So maybe look up the equation for kinetic molecular theory and bring in one of the values. That value might be concentration, it might be number of molecules, it might be speed based on temperature. That's something that would be interesting. How about we put that down? Molecule speed based on temperature. And now this is starting to turn into something that I would consider more of a machine learning project than just a stats type thing. And then these concentration we can get from the research and scientist. Number of molecules, that's something that we can calculate for and embed. However, kinetic molecular theory, I'm having to look this up. This is going to be an external data source that I bring in, not only the data source, but also the knowledge base. And I guess you could say here too, but I already know you just have to multiply by Avogadro's number and you'll have the number of molecules. But that's something that we might want to pull in a paper for to support, this is why we did this calculation this way. And then this is going to be really interesting if I can calculate for the molecule speed based on the temperature present and the concentration. I think that's something that's possible. And then we have a pretty good spread of external type data sources. These are, generated, well, these will be generated from the current data. Something that's external that's completely different than them being reliant on our current data set. That's a little bit more complicated. I think bringing in kinetic molecular theory is great. Something that is not currently present, I'm thinking things like, atomic mass is not currently in our data set, and that's something that's different than our data present. But that goes back to like number of molecules, right? Something that we could pull in, and that what's hard is like this. I want to say bond. I don't want to say bond angle, but like maybe reaction angle or something, because bond angle is something very specific, and that's not exactly what I'm looking for. Let's do collision. That's a little bit better. Collision angle. Not collusion. Collision. Collision. Thank you. Collision angle between solvent and solute. That's going to be the same no matter how many molecules are present. Something that might be different is hydrogen bonding or van der Waals forces. That's something that we could calculate for that's not presently in the data set. Would be van der Waals force. That would be really interesting, especially because we have this alcohol group that is approaching this ether. Technically, it's an ether bond, even though it's hazy because bicyclic rings and stuff. But yeah, there's an ether bond and an alcohol group, and alcohols and ethers do, in fact, react. So it would be interesting to me to pull in van der Waals force type calculation. Now, is that something I've calculated before? Yeah, like once, like 12 years ago. So definitely going to need to bring in a paper, bring in an outside. I think I can find all the data, but we might be pulling in like, let's just say general periodic table data. And something else that we might need is what is it called? It's called shielding and or electronegativity. And while it's going to be the same for everything, I'm curious to see if there's something that relates this idea of periodic table data, atomic mass, and or shielding, and or electronegativity data, and concentration. That would be really, really interesting to pull into this project. Do I think that these things all play a part? And the things that I saw, which were two separate oily mixtures, Absolutely. I do think that these played a part. It's just I don't know to what extent. And I think pulling them in and doing a little bit of machine learning, doing a little bit of a regression, um, would inform about that. So here's my external data sources. Let's actually put, let's do periodic table trends and concentrations effect on them. Let's do that. That way I can know to look up that specific relationship in the future. Because right now I'm kind of just talking about it, you know? I'm just spitballing. So that, this is the reason why I said that this card size was 2. Uh, Everything that I just talked about out loud is usually something that a data scientist is going to have to go to a domain expert and ask them about. Like, hey, I noticed that we have temperature data. Is there anything in your realm of expertise that could cause, the end thing that you're looking for that's associated with temperature? And immediately I would go to like KMT, I would go to molecule speed. Those are things that I would automatically go to as a researcher, as a scientist, but not necessarily as someone who works with data. Things that I would think about as a data person would be, I can see that temperature is a function of time here, but why? I can see that concentration is also a factor here, and it's outside of time. Um, what are some things that connect concentration and the temperature effect that I'm seeing? That's kind of how I would phrase my question to the researcher. And these are the things that that researcher might say back, but that could take a whole hour conversation in person. So let's go ahead and add this discuss external data sources. I forgot we were. Uh, can I not? Yeah, copy. No, I don't want to copy the card. I just want to link to it. Where's attach? Do I right click? Copy. No. Ugh. It's probably like right here, directly in front of my face. Actions. Copy link address. Does that give me the card link? Or do I do it here? Add an item. And I'm adding myself. And then can I... What does that do? Yeah, it does exactly what I want. Okay. And I expect this to take, half an hour. And I'm going to add this card size. I'm going to add 2 story points. Now we just spent those, so I'm going to save. And we check this off. That's not what I meant to do. I meant to kind of go through these and add the story points and add them to a sprint here. And I know I talked a couple of sessions ago. I don't know if it was this stream or another stream. It's all kind of running together in my head. But we want this story points here to equate a work week. I'm putting some time estimates here. Right now we have about 6 hours, so that's about 1 work day. And we want to have a minimum of 2 weeks. So these sprints are 2 weeks. And I know you're seeing this and being like, that's 2 weeks ago. Yeah, I'm also streaming, so things get, time dilation occurs. Find external data sources. So with this, this find external data sources, I want external data is alongside that raw interim data. I want to obtain that external data. So this card size I'm going to put as an 8. Will it necessarily take that long? No, but it is going to take a lot of reading. This is going to take a lot of reading. Copy link. And I'm going to put, I'm going to put a whole day on this. 8 hours, because that's about, honestly, what I would spend as a data scientist. I would spend around 8 hours doing this particular task. It's a lot of story points. Discuss future model structure. This is something that's pretty simple to do. I'm going to put a card size of 2 on it. And, oh, share. Copy link to card. Oh, that is so much better. I knew it was just hiding from me. It was right there in front of my face. This is going to take maybe an hour. So I think I say discuss it, right? Yeah. Yeah, so I'm going to look at a couple of different things. Okay, next page for the music time. Okay. And then find information on different regression types. This I'm going to give a solid half day. Like, this is going to take a little bit of time. And it's going to take, around a half day to do. So at Ian Fawcett, I'm going to put 4 hours on this. The reason why is because we need to look up stuff. And that's the big thing, is whenever you have to look up stuff, that's like dedicated thinking time, right? Find information on deep learning model architecture for regression style data. I'm going to give this another 4. And this is something that we want to do before we move on to this next step scrub here. So that's 2 days. This is around 3 days of work. I want to try to get another half day in this sprint. However, I think I'm going to leave it here before moving on. Story points, pull down data from database. How many story points did we gave that 4. Hold on. So 20. $20.16. $14. $12. $4. And then I said we're not gonna do 2, but find information. We're gonna add that one. So this just needs 4 more story points. That's what I was trying to figure out. We have 12 remaining. We have this 4 on different regression types. We have that. We have those 4 remaining, and then we have this find external data sources, which should be 8. I believe something has happened with my story points here. Okay. I'm actually going to change this name, 2023 to 221. Let's 0 this out. Okay, and on here we had pulled down data from database 4. So let's go ahead and add those 4. Save. Done. And then we had create space for data and transformations, another 4. Okay, cool. And then we had determine what data is available in files. That's 2. Discuss external data sources. This is something that we're going to go ahead and update to done. We did it together. It had 2 story points associated with it. Save. Okay. And then the next thing is find external data sources. That's 8. We still have that remaining to do. There we go. And discuss future model structure. 2 story points. Find information on different regression types. That's 4 story points. So let's go ahead. 1, 2, 3, 4. And then find information on deep learning models. That's another 4 points. Okay. Okay. That looks a little bit better for a sprint to me. Even though I have some hour estimation, I want around 30 to 40 story points worth of work for every 2 weeks. So let's go ahead and get started on some of this stuff. I know that we already did one of these, discuss external data sources. The next thing that I would like to do is actually future model structure. Okay, so here we know that we have linear type data. And by linear type data, we have some raw examples of a graph here. And while it's not linear, we do know that we have 2 different variables that are moving by floats. And whenever you have 2 variables moving by floats, let's go ahead and title this discuss future model structure. And we want this to be a header. Okay, so we have 2, this is our raw data starting point. We have 2 variables that are both float type data that are directly correlated. Correlated. How about we try that? Two variables that are both float type data that are directly correlated, meaning as time moves on, temperature will change. Will it go up or down? That's dependent on the amount of time that has passed. That is the design behind the particular type of experimentation that was completed, which was done using a gas chromatograph. So, future model structure. This means, since this is the type of data present, that means that a regression will need to be evaluated. So we have a regression to start. And then I know that we just discussed a bunch of different other features that can be added. Using machine learning, we can do a regression with multiple features, not just temperature, which is pretty cool. But it also means that, we might want to, since other features might be added, and ANOVA. So this is the type of statistical test that are directly correlated. In statistics, an A/B test should be completed. That's comparing one thing directly to another. Since other features might be added, an ANOVA statistically should be considered. But, this isn't a classification problem. I think I should put that. This is not a classification problem. So that means no random forests or clustering should be done in the realm of machine learning. I do believe, and I'm gonna pull it up on a different screen over here. I do have a list that I made myself. Yeah, here it is. Oh no. I don't appear. Wow. That's really funny. Okay. Okay. I'm gonna do a thing right quick. Off camera. Okay, cool. I have found the file location. That's good. Okay. CD. I'm wondering, yeah, it's not in the README, which is unfortunate. I need to go back and just fix all of that. Let me see here. I don't know where that is. Let's see here. Let's see if I can find it. I have this file somewhere. It's not loading on my reference screen. Yeah, I kind of had a feeling that would happen. So that's something. But basically in it, I have this big long list of all of the different types of machine learning. It loaded this time, and there's a couple of different categories of machine learning. It's one of the big things is, is it supervised or is it some unsupervised? Do we have labeled data or not labeled data? So let's actually start. So this is kind of just like me rambling, right? But to actually prove this point of which model we should use, this data is labeled and should use a supervised machine learning method. What that means is we should not use any sort of clustering. We don't need to use k-means or hierarchical or anything like that. We should use a supervised machine learning method. Also, additionally, this is not a classification problem, so regression should be used. And regression means something in statistics, but it also means something in machine learning. So we should use a regression in statistics, but we should also use one in machine learning, and we need to look at a couple of different options. One of them is using a support vector machine or an ensemble method, which just kind of strings together a whole bunch of stuff, which is kind of what a support vector machine does anyway, to evaluate the different features. And it says here that you can use a decision tree. I don't think this is a decision tree kind of problem, because it's not if, this, and. It's more like, where are we at on this I already identified spectrum? So since this is a placement along a number line type of problem. A decision tree should not be used initially. However, should evidence point to the separation of material, meaning there is evidence to support that a reaction took place between the solvent and solute, then at that point a regression, or not a regression, a decision tree such as a random forest might be helpful. So this kind of helps us figure out where we should navigate first, is kind of looking at the specific parameters that we're dealing with. We're dealing with two float variables that have a direct relationship with each other. That means also the data is labeled. We know what the concentrations are, and that's something that makes each data set unique and different from each other. So we have labels. We should use the supervised method. It's not a classification problem, so regression should be used. However, at first, if we end up with two different concentrations of something, then a classification might be in order to figure out, you know, reacted versus not reacted. And also, I would say, also using a neural network is in order regardless of study results. What I like to do for neural networks, and aka deep learning, is I use them as kind of like a so neural networks are great and they're inexpensive to use individually. However, I like to use my neural network as kind of like comparing it to, you know, the best not neural network I can make using traditional machine learning approaches. And if the neural network can significantly outperform those traditional approaches, I kind of use that as a proof of, yes, you should spend all of the computation costs that's associated with neural network and all of the calculations and computation and overhead that's going to come with using a neural network, because it is this much more accurate or precise or whatever. But if there's no statistical difference between the performance of the two different types of networks, despite me training and tuning the neural network to the best of my ability, then at that point I would say, hey, just so you know, I did use a neural network, but this other machine learning approach kind of outperformed it or performed at the same level as, and it's computationally cheaper. So that's just something of note. I like to research and develop with neural networks, but I don't always like to deploy a neural network into it's an expensive thing to have, so I don't always like to deploy on a neural network. So there's some other stuff that happens with these considerations. Now, in a regression, there's a couple of different types of regression. One of them is called a cart tree. And then there is decision trees. The cart tree is a very specific type of decision tree. but we also have a decision tree. And I said it's not a classification decision tree. It's not, it's not an if and then. It's what happens is decision trees ultimately, whenever they're predicting a line, it's, does it fit on the line or does it not fit on the line? If it fits on the line, continue forward. If it does not fit on the line, do not continue forward. That's what decision trees do. So they basically make so ultimately machine learning is just solving for a complex equation. Basically each feature ends up being a coefficient of a variable that is equal to y, which in this case our y is our concentration. We're solving for y, basically. We need to get to the concentration. That's our target variable. And we can use temperature to do so. The idea of temperature and time together can be used to do so. So time is going to be, one coefficient, and temperature is going to be another coefficient. Some of the other things that we discussed earlier today, number of molecules, molecule speed, those are things that could be used to figure out the concentration. So on the decision tree, it basically, depending on the parameters that you set up for each feature, what it does is it takes those parameters and basically it makes a list of possible equations. And if, you start in the average or the middle or something for each feature, for each coefficient. And if it gets closer to the truth, then with that particular coefficient, then what happens is the machine learning algorithm will select for something that is closer to that number each time in lieu of something that's further away in this range that you have predefined. And you can do all of that, and it's called hyperparameter tuning. And you can figure out, you can tell your machine learning algorithm how to train each feature, and that's hyperparameter tuning. And you can do it using a variety of different algorithms. Like I said, one example is start in the middle and then move up from the middle, but you can also start at the lowest value and move up, and there's a whole bunch of different ways. Okay, that's cool. Hyperparameters and tuning, and then here, okay. I think that's all that I have listed in my little cheat sheet is cart trees and decision trees. Those are not the only things. Basically anything that you can find, and let's go ahead and pull up the scikit-learn documentation, and let's see if we can't find all of the regressions. There's linear and quadratic. Linear regressions is what's standard in the scientific community to begin with. It's standard in statistics. There's also kernel ridge regression, then there's support vector machines, there's stochastic gradient descent. I would be very interested in this particular type of machine learning tool. And the reason why is because we're trying to find a spot in which concentration deviates. And gradient descent means we're looking at a spread as we move down, right? And then stochastic is the method in which we're moving down. So I would be very interested to use this stochastic gradient descent. Now, music is instead, or it is still going, but it's like ambient background music, which is kind of nice. Then there's this thing called nearest neighbors, which I'm not really terribly interested in. I am interested in using the Gaussian processes. There's cross decomposition. This is probably going to be really helpful in figuring out, which features are being used and which ones aren't. Then there's decision trees, which we've talked a little bit about. Then ensemble methods kind of add them together. Gradient tree boosting, I'm extremely interested in. Histogram based boosting as well, because our starting data, number one, it just looks like a histogram. It has this weird curve thing going on, and there's a lot of correction that we can do that might make this look a little bit more like a histogram. And then we feature selection. We're definitely going to be going through some of this. Hold on, I am going to mute my mic for a sec. Oh my goodness, you know when you talk for a long time and you forget to drink water and then you have to cough? That's what just happened to me. Isotonic regression would be really interesting. Then there's probability and then neural network. So these are all things that I'm going to, and naive Bayes as well, especially the Gaussian or the multinomial. Not really Bernoulli, not really categorical, but there are reasons why I'm saying these particular machine learning methods. Um, these are all things that we're going to want to go through and do some calculations for. So here, as far as discuss model and structure, let's do, it's labeled. We should use a supervised machine learning, a supervised, and let's actually get that bolded here. And we want to use a regression. Support vector machine or an ensemble let's actually swap this up a little bit. Because those are kind of like the end ones. Let's see what happens first. Since this is a placement along a number line type of problem, a decision should not be a decision tree. Tree should not be used initially. The first thing that we're going to want to do is a linear regression. First, a linear regression should be evaluated along with there are a couple of others, kernel ridge, and then I know in here I have a lag planned where I look at linear ridge and kernel regression, or linear ridge and kernel ridge, along with let's do ridge and kernel ridge regressions, just to figure out, how the data is looking. We will probably end up doing a lasso. Now, a lasso is something that you apply to a linear regression. This ordinarily squares OLS. I like stat models OLS a little bit better. We'll see that here coming up. But we're going to want to start with the OLS. We'll also want to do a ridge, and we'll want to do the kernel ridge as well, which is kind of separated out. Then we have discriminant analysis. This could be really interesting. Dimensionality reduction. We should mention that here. Dimensionality reduction should also be considered. And the reason why dimensionality reduction is just what it says. We think that we're looking at a linear problem. However, there's some complex interactions that are happening between our concentration and the temperatures that we're seeing, and the results that we got as a result of making these solutions in the first place. So there might be more going on than we expect, and dimensionality reduction can kind of expose that type of behavior. Then we also want to look at a support vector machine. Lastly, a support vector machine or an ensemble method should be evaluated. And then we get into some other stuff. Placement along a decision tree should not be used initially, however, should evidence point to the separation of material, dimensionality reduction, some other stuff, like basically this is not linear. A decision tree might be helpful. And then a neural network as well. So the big thing is regression and neural network. After we start in this field of regression, which, you know, linear and then ridge and kernel ridge, then some other things, PVA, dimensionality reductions, those types of things. And a neural network, we can kind of get some additional information about SVMs and other ensembles, or potentially stringing together several different machine learning architectures or pipelines. So this I view as a good start for model structure. That means our data, we are going to structure it so that it can be fed into a regressor. And this discuss future model structure part of our sprint here. Let's look at the card. Discuss future model structure so that time to transform into the necessary data structure for that type of model is reduced. We know that we want to look at first an OLS, and I'm also going to bring up stats models. And we're going to go to the user guide, and we are going to go to the linear regression setup. And this stats models regression, you know, it does an OLS. You can see here we have an OLS output. We get OLS regression results. So, okay, cool. We can also do weighted least squares, generalized least squares, and auto-correlated AP error least squares. We can get some different commands and arguments for doing each of those. But here, let's see, we need to do the stats models. Then we load in, they are loading in the data set here. They're adding a constant data set from a different location. And then here, they're just calling on stats models, the library. They're calling on this function, this OLS function, and they are pulling in this endogenous and exogenous data. This means, you know, intrinsic to the original data set, and this is outside of the original data set. And they're comparing them and figuring out if they have any sort of correlation. That's pretty cool. So what we don't see here is what this data looks like, but we do know that they have their internal and their external, and they're comparing those two things. So we know that we need to set up an a y variable and an x variable, aka our target variable, and everything that is not our target variable. That's kind of what this is telling me. And then at that point, we can get a fix. And we can get a detailed example. This might give us a little bit more information here. Yeah, here we're getting some artificial data. We're getting an x and a y, and then they're setting up a random. They're adding a constant. That's their intercept value, and then they're plugging it into this formula to get their target variables. Our target variable in this case is our concentration. we want to identify our concentration. And I think here in this particular space, I said communicate data structure. Each file is different run, 2 columns of data, time and temperature. So in this case, our y would actually be the temperature, and our x is the concentration, because concentration is our independent variable. I'm actually going to change this. Concentration is the independent variable, while temperature is the dependent variable. Time is a constant. It's changing, but you know, it's not changing as a result of our experimental intervention. So this has been updated a little bit. Here I put time as the independent variable and temperature is the dependent. What I meant was temperature is the feature while concentration, and I never said this, it didn't even occur to me until last week that concentration is also a feature that we need to include. It's what we're trying to solve for. That is our target that we're trying to get to, is we're trying to solve for concentration. Okay, so that's something here. Future model structure. I'm going to put that concentration is the target variable. So this is like data science talking, right? Everything else, including time, is a feature. Including time and temperature is a feature. Basically, these are things that could be used to calculate for concentration. That's really what we want to get at. We want to get at concentration. So time is a feature, but temperature is dependent on time, which is independent. It's something that we don't change. So that interplay between words, data science, and this is something that I struggled with for a long time whenever I was career transitioning from this world of science into data science. It's something I struggled with in school a lot, is this idea of dependent and independent variable is still thrown around a lot. So in data science, I identify the target and the feature. And sometimes the target is your dependent or independent variable. It's not always, though. In this case, concentration is independent. It's what we did to make an adjustment, and temperature resulted based on the concentration that we did. So I prefer in data science to use target and feature, because those are something that are very specific to data science versus science. Okay, cool. So we have discussed future model structure. We have that here. I'm gonna add that to concentration is the target variable. Time and temperature are features. Any external data would need to be a feature and something that is a function of concentration. What that means is concentration has a bearing on it at all. Changing the concentration can change the feature. It doesn't necessarily mean that it was present during that experiment. Like, I didn't calculate the number of molecules during that experiment, but it doesn't change because number of molecules is a function of concentration. Pulling something in like kinetic molecular theory, which temperature is a variable for, if we can find or identify what all of the other variables would need to be for kinetic molecular theory, we would be able to include velocity as one of our features. And velocity is a function of meters, it's space per second, right? And so that's something that's really cool. Number of collisions is also something that we might be able to add into. That's like something that you can calculate for. Number of collisions. And that has to do with kinetic molecular theory. Cool. Okay. So here we have changed something. I just hit save. And let me pull up my, is this it? This is it. We should be able to see what has changed here. We've changed some stuff, so we're gonna add this to our change log. Then we're gonna make sure that it posted. Great. Now we're going to add that forever. Add discussion on future model structure. And this is something that we will always be able to refer back to. And I think that that's pretty cool. Okay, so we were able to discuss future model structure. That has been complete. Let's go ahead and spend those 2 story points. And let's spin them here as well. Okay, now find information on different regression types. We already looked a little bit at stats models. We looked at OLS. So let's go ahead and here find information on different regression types. So we know that we have OLS. We know that we have, and this is ordinary, let's do ordinary least squares. And that means things. Then we have linear. We have the ridge. Then we have kernel ridge. Let's see what else we have here. OLS here, we can see the linear regression. We have, it works by, we have a fit. So we're adding these points to a line, and then we can find the coefficients for that line. So we're setting up our linear model dot linear regression. So this linear model is from sklearn. Then we are using the method linear regression, and we're setting that up as a variable. Then to that variable, we are applying our data set, and then we're calling on the method again. And then we want to call on the method and get the coefficients. Then we have ridge here. So ordinary least squares fits a model with coefficients to minimize the residual sum of squares, a chi-square test basically, between the observed targets in the data set. So that's kind of what a OLS is it takes a chi-square, or the equivalent of a chi-square for machine learning versus statistics. The ridge regression imposes a penalty on the size. So the larger the coefficient, the more that it's penalized. And then they minimize a penalized residual sum of squares. And then this is a ridge classifier, which we don't want to do. Ridge complexity, that's great. Ridge CV is probably what we'll want to use. Then there's a lasso. That's something that I'm interested in applying. And then there's information about using cross-validation, which is basically how you check for accuracy of your model whenever you are regressing. There's a multitask lasso, which is going to be interesting. Then this elastic net, a linear regression with both L1 and L2. So these are lassos. Combination where the weights are non-zero while maintaining the regulation properties of the ridge. Okay, so this would be interesting. We can look at this elastic net. And I'm going to put here in sklearn. It applies ridge mechanics to a lasso. Then the multitask, sparse coefficients for multiple regression. Okay, least angle regression, a LARS, is not really something that I'm interested in doing. It's a kind of similar to Ford stepwise, finds the most correlated with the target, multiple features having equal correlation instead of continuing along, it proceeds in direction equal angular between the features. Basically, this will work if you know that your stuff is going one direction all of the time. Is it always getting bigger? Is it always getting smaller? Are they around the same impact, or do they have the same place value? And that can be really helpful in certain circumstances. The Lars lasso is something that I'm a lot more interested in. But I'm not really interested in any of that. Bayesian regression includes regularization parameters. Regularization, that's a word. The estimation procedure. The regularization parameter is not set but tuned to the particular data at hand. Uninformative priors over the hyperparameters of the model. They use an L2 regularization, which is used in Ridge, is equivalent to a maximum posteriori. Yeah, basically it's just saying, hey, we add a lambda, which is kind of like adding a coefficient. So that's going to be Bayes, or Bayesian regression. The advantage, that's great. The disadvantage, inference of the model can be time consuming. And that's basically what I was getting to here, is it's just complicated. Bayesian ridge regression. So that's why I want to definitely evaluate, a linear regression, a ridge regression, a kernel ridge, is because, all of these things look at ridge stuff too. Like, they implement ridge mechanics. So if a ridge regression outperforms the OLS regression, then I know that I can probably move forward with some of these specializations that include ridge mechanics. But if the ridge regression is much worse than the OLS, then I probably don't want to use anything with ridges. Kind of linear, which is very similar to Bayesian, but leads to sparser coefficients. Logistic. Yeah, logistics is for classification. That's not what we want at all. And here we get some information on, like, the Poisson and gamma and inverse Gaussian. Like, these are all different equations that are used to, it's kind of like determining the step that your regression is taking. Normal is, y minus y squared. That's ordinary least squares. Bernoulli takes some logs and does some stuff. Categorical, we're not interested in. Poisson takes some logs and also does some y's and stuff. Then gamma, you can see, takes some logs too, but it doesn't apply our target variable as often. Then the inverse Gaussian looks at some squares, but also does some other stuff too. And then we want to look at probability density for all of the things that we do. That's another metric that determines how well our models are performing. I mentioned being very interested in the stochastic gradient descent. Yeah, number of samples and the number of features. Our number of samples in each data set, number one, we have 64 different data sets. And let's see if we have an end here. Like, how many rows of data do we have? I know that this is about 3/4 of the way done. We have around 1,000 rows. That's not too many. Big data is considered 5,000. But we have 64 of them. So this stochastic gradient descent is something I'm very interested in, because you can do the partial fit. That's what I'm very interested in. Partial fit kind of just like throws a monkey wrench in and says, hey, what if this is the most important? And then the next time it does something completely different. It's what if this other thing is important? And you can also do the regressor. And then you can do different loss functions. Loss is being log or exponential or kind of, whatever the trend of the data that you have is, you can kind of set up with the shape quadratic, or, you can set it up with that shape. Then here we're starting to see that stochastic gradient descent is like this in-between method between an OLS or a ridge and a support vector machine. And it's really the only thing that I can think of that is in that weird in-between space. It doesn't mean that it is the only thing, but it is something that I'm very interested in evaluating. It's, I guess you could say it's like the first step. I don't want to say it's the first step out of statistics and into machine learning, but stochastic gradient descent is something that is the computation is very difficult to do on older types of computing. So a perceptron. Didn't realize sci-fi was happening here. Then robustness regression is good at outliers and modeling errors in the presence of corrupt or error in the model. So if we end up with something super error, then maybe we want to do this robust regression, but I don't foresee that really happening. Quantile regression estimates the median or other quantiles of y conditional on x, while OLS estimates the conditional mean. So cool. A quantile. Okay. This might be something that, predicting an interval instead of point prediction. So what that means is, let's identify an area where our solute is no longer acting as a solute, but is acting as a reactant. So this might be interesting. And I'm going to put here I have my list. This is kind of like the normal stuff that I would do. The project specific consideration. So this is just normal that I would do just because this is a regression type problem. But this quantile regression is project specific. So that's something that I'm going to look at as like a special case, right? And we know that we have an L1. Anytime that you see L1 or L2, that means they're using a lasso. And we talked about lassos kind of at the beginning of the page. Then we have polynomial regression, nonlinear functions of data. So this is something that we definitely want to look at, is this polynomial regression as well. So we might be adding in some things that are not exactly linear, whereas our temperature is supposed to be linear. The whole reason for this project is I found it to not be linear. So this polynomial might point to y. Okay, so that's it on this scikit-learn page for the linear models. If you remember, that's not the only thing that is here. This kernel ridge is completely separate. It takes a ridge regression and classification, which is interesting for this particular project because we're trying to identify, is it solvent or reactant as well. However, that's not labeled data for us. So, kernel ridge performance might point to, if this outperforms a normal ridge regression or a normal OLS, then that might point to we have the addition of something else going on. Okay, and then we have support vector machines, which I do believe are already on our, no, they're not. Okay, support vector machines, and I have a kernel ridge already in my general list here. This is our linear models. Let's get rid of that. Stochastic gradient descent we have in our list. Nearest neighbors is classifier. We're gonna wait on that. Then Gaussian processes. Let's look at some Gaussian. Supervised learning method designed to solve regression and probabilistic classification problems. As the concentration increases, it is more likely that there's a reaction because, there's more stuff around that's hitting each other. And that's what you need for a reaction to take place. That's why I was interested in Gaussian process regression. So that's going to go under this project specific. So I have the quantile regression. Let's do Gaussian Gaussian processes. We want to look at a Gaussian process regression. And these are, again, project specific considerations. That means that I have hand-picked these particular things for machine learning. And then here you can see that there's a kernel for Gaussian processes as well. So if we see that our kernel ridge does better, maybe a kernel Gaussian process will do better as well. Then we have cross decomposition. And you can see here we have a regression that's part of cross decomposition. It's supervised estimators for dimensionality, reduction, and regression, partial least squares. So this is moving away from kind of traditional linear type stuff. And we have this regression here. So we have this initial algorithm. Then we have the power method. So basically that's applying the power series to our equation to figure out if it's informative or not. They're approximated using the projection of x instead of the projection of y. Loading computation is different. The deflation will be affected. Okay, that's a lot of stuff. Modifications affect the output of predict and transform, which are not the same. Components is limited by men, samples, features, targets. The rank is samples and features. Okay, that's good because for the regression, we only have one target. Single targets, multiple targets. So this is like a lasso. Regularized linear regression where the number of components controls the strength of the regulation. What that means is the more features that we have, the more weighted, or the more our weights or our coefficients are affected by the number of features present, meaning they'll be smaller. It's likely they'll be smaller. So this PLS, this cross decomposition, partial least squares, I'm going to put it here. It's not something that I would say is going to be super helpful in this project. I'm going to put partial least squares decomposition. But I do want to see how it will affect, or what the effect of our data is on by using this particular type of algorithm. Then we have the naive Bayes, based on Bayes' theorem, conditional independence between every pair of features given the class variable. Okay, so basically it's saying that our features are related. And in our case, that might actually be true. Time and temperature are not related. But if I pull in number of molecules, then they are related. And using a Bayes type regressor would mean that we are maybe accounting for that particular bias. So we might want to look at which type of Bayes to use. I already know multinomial is not probably what we're going to end up using. Gaussian would be something appropriate. Bernoulli, that it's, Bernoulli means like zeros and ones. It only has two things. It either is or it isn't. So I don't think a Bernoulli naive Bayes is going to really work. This complement, I don't think that this is going to work. I don't think the multinomial is going to work either. We're not categorical. Then out of core, Bayes model fitting. I think the Gaussian is probably going to be the best one. Okay. There's also some issues with this out of core model fitting with scikit-learn, and that's kind of what's discussed here is partial fit. It has some specific formatting issues for our target and our related features, and that's what it's discussing in this section here. So I don't think out of model is going to work, but maybe a Gaussian naive Bayes, and I'll put that here. And this is it's for classification. That's not exactly what we want. Yeah, it's a decent classifier, but it's known to be a bad estimator. That's not exactly what we want with concentration. But you know, it might be good to have some light on some stuff with, you know, is it reacted or not reacted? Then we have decision trees here. And we want to look at the regression decision tree. So decision tree regression. This is kind of how I start. Like, I go find all the things that I could use, and then as I go through time, then I kind of eliminate based on that. With several outputs to predict, so we don't have a multi-output problem. Some complexity and tips on practical use. CART is one that we mentioned. Then we have ID3. I remember ID3 and C45 and C50 and all that stuff. So CARTs would be good. So no categorical variables. I wasn't planning on including any categorical variables, so that's good. Successor to the ID3. The ID3 is what I was trained on. Must be categorically, dynamically defined, a discrete. Oh, that's cool. Okay. So I would still say out of all the tree algorithms here, CART is probably going to be our best option. Decision tree, and then a CART regression. Mathematical formulation, minimal cost complexity pruning. This is going to be a big thing in the future. Okay, then ensemble methods. Here, it's probably going to be like gradient tree boosting or this voting regressor. So I'm just going to put ensemble methods here in my list. And then we don't have any multi-class or multi-output. We definitely want to do some feature selection. Definitely want to do some feature selection. Self-training or label propagation, that would be interesting for determining, you know, reacted versus not reacted. Probability calibration, and then we have neural networks. This is moving into the next kind of topic. So I'm going to hit save here. We have our project specific. The ones that I've picked out are quantile regressor or Gaussian process regression. Those I think are going to be the highest yield for what we're testing out. I definitely still want to do a linear and a ridge and a kernel ridge lasso, an OLS to start. And the OLS is kind of like, okay, we're doing a regressor. You basically develop your machine learning model OLS, and then you try to outperform that OLS. That's like your benchmark. So we definitely are going to do an OLS. I want to do a linear, I want to do a ridge, also want to do a kernel ridge. And then I want to use what I learn between comparing those to each other and to the OLS model. I feel like those things are going to I also want to do a lasso, honestly. Those are like the first 5. I just want to do those 5. They're all pretty low computation cost. And the reason why I want to do those is because those mathematic principles are used in the quantile regression and the Gaussian process regression and the stochastic gradient descent and the and the SVMs. They're the ideas and principles that are used in these more simple type machine learning models will help us hyperparameter tune later on to some of the more advanced and maybe more computationally heavy things. And so those are things that I want to look at first. So I want to note here, I have this listed under code because I knew I would be going to the documentation for these things to figure out what was going on. Now, stats models does not have a ton of regression models. We've got the linear regression and robust linear models. They're not, we talked about robust earlier. There's an ANOVA, which we've mentioned, but they don't really have the other types of modeling that we were looking at on scikit-learn here. The list isn't exhaustive, and the reason why is because stats models is ultimately a statistics library that's used to inform about machine learning. So let's look. Let's do stats models. Classes and functions for the estimation of many different statistical models, not machine learning techniques. They do have some overlap, and I want to start with the OLS and stats models because that's our baseline normal thing that we're going to be springboarding off of into other things in the future. Okay. Next music page. Okay. So that's kind of what I have to say about stats models. Then find information on different regression types. These are all the different regressions that we could possibly use on this project. These are the ones that I pulled out from the list here that I thought would be most pertinent to our project. And that's because I've done a lot of these. I won't say that I've done all of them, but I have looked at examples for all of them, and I know the project scope. And so those are the ones that I think would be the most useful. And then here, find information on deep learning model architecture for regression style data. First off, we finished this. I am calling this done. Find information on different regression types. Yeah. I will have information already identified on which type of machine learning is necessary and additional resources on model type. I guess I can post this link here because that's where all of my information is coming from. And I've already identified like which things in this particular page on scikit-learn are going to be, you know, the ones that I want to evaluate. So I'm calling this card done. We have spent to those 4 story points. This was different regression types. I'm calling that done. Let's go ahead and put in those 4 story points. Cool. Find information on deep learning model architecture. So that, I believe, is here. Neural networks that are supervised. So right now we are working on best practices for deep learning regression type data. I just want to start with the documentation, and you start with scikit-learn to do neural network type modeling. Okay. Multi-layer perception, or perceptron. We already looked at what a perceptron was, and so we'll be pulling that idea into this model. But notice I didn't really pick out the perceptron for our regression. And there was a reason for that, and it's because of, you know, the algorithm for the perceptron was very similar to the OLS algorithm, and I wanted to explore different kinds of algorithms, so I didn't want to have overlap. I didn't want to do 2 of the same thing. But it can learn, in this particular case, this perceptron can learn a nonlinear function, and that's what I'm interested in for either classification or regression. It's different from logistic regression, which is a classification type regression. In between the input and output layer, they can be 1 or more nonlinear layers called hidden layers. And this is kind of where neural network starts. You have your features, you start with a list of your features, and then you do something to them, and that's called the bias that you're introducing on that layer. And then you have an additional layer where you have another thing that you do to it, and then you have your generated output, which is your target. You're trying to calculate for your target variable. And hopefully you get closer, and if you don't, well, then that particular node is weighted against so that the model doesn't choose that node. Each of these dots on the screen are called nodes, are not selected for in the future. So we want to do regression. NLP, multi-layer perceptron regressor, implements that uses backpropagation with no activation function in the output layer. That's important, with no activation function in the output layer. That tells us something about the architecture. So first off, we're going to go here, and we're going to say that scikit-learn, or sklearn, has a multi-layer perceptron neural network available, and it I guess I just highlighted it, I didn't copy it. It has no activation function on the initial layer. That gives us some information about architecture, which is what this whole thing is about, is how do we set up, how do we make this, how do we do this, how do we get from, what bias do we introduce, what do we do next? That's what the architecture is for. It can be, which can also be seen using the identity function as the activation function. I'm going to put that as well. But can use the identity function on the activation layer. Also supports multi-output, but we don't want to have more than one target. So we're going to open this up, because this is regularization, and it talks about this parameter called alpha, which uses L2. So this is information about our lasso, which helps in avoiding overfitting by penalizing with large magnitudes. Okay, cool. So we do want to use an alpha layer. So we can, I'm going to put here, what do they call that? They called it parameter alpha. May use a parameter alpha to do L2 style regularization on the data to mitigate or penalize larger values. Okay. Algorithms. We can use a stochastic gradient descent, an ADAM, or an LBF-GS. I'm guessing GS is gradient descent or something, maybe not. Okay, so we can use a variety of algorithms. This is kind of why I want to evaluate the stochastic gradient descent. If it doesn't work well, then I want to look at an ADAM or this LBF-GS. I've never seen that before. I've seen the ADAM before. It's similar to stochastic gradient descent. and that it has a stochastic optimizer, which means it goes stepwise, but it can automatically adjust the amount to update based on adaptive estimates of lower order moments. So basically what that means is if something is happening a less amount of time and it has little impact, then it's going to move strongly away from that. So it kind of throws something in that's kind of random, and then it'll move from there. It's a solver that approximates the Hessian matrix, which is not a math word we've seen before, which represents the second order partial derivative of a function. Okay, so there's some chemistry stuff here at play that I'm aware of. I know that this relationship between my concentration and my temperature here is not direct. I know that. There's no direct relationship because whenever I did a regression on the initial data, the R squared value was like 0.08 or something. It was ridiculously low. So I know that this is not a first order derivative relationship. Could it be a second order, something that's more quadratic in nature? Well, I did fit some quadratics onto my standards curve that I eventually created. That didn't perform well. It performed better, but it still wasn't good. So I am very curious about this Beefer's LBFGS type equation. So here I want to add a note here that you can use the stochastic gradient descent. The atom, and the atom, it said, online and mini batch learning, that's good. But it automatically adjusts to update parameters. So the atom uses adaptive, that's kind of funny, adaptive approximations. That's probably where they got the word, or the abbreviation atom. And then there's the L Beefers. I'm not gonna call it that forever, but it's kind of funny to me and it's helping me spell it. The Hessian matrix. So this already tells me, like, I want to go look up what the Hessian matrix does, because that is interesting to the problem that I have at hand right now. So I want to do a deep dive on what the Hessian matrix is, and that's something that I'm going to do off camera. And uses this matrix to do, want to make sure I get the parameter updates. Yeah, to perform, to do parameter updates. Which is, all three of these kind of have a different way of updating the coefficients associated with the features. And so based on your problem and what you think is going to help you arrive to your solution in the fastest way, that is going to tell you which type of, what do they call these? Solver. Which type of solver that you want to use. Quasi-Newton methods, that already to me is pretty cool. Okay. Okay. Now, complexity. This talks about layers. So we have so many hidden layers before we end up at our target variable, right? And this is kind of what I wanted to... You can calculate how many... This is kind of what it's telling you, is you can calculate how many layers that you should do. We don't have binary classification. We have n classes, so We have a softmax to the in classes, and it does things. Um, and then we introduce a loss. So this is already telling me, okay, so I already want to go to this page here, which has the NLP regressor. And if I'm right, there's a lot. Each one of these parameters we have to figure out. Yikes. And which activation, if we want to do identity, logistic, Tanu, Relu. The default is Relu, but we've already been told for the multi-percepton, which is what we want to do. We want to activate using the identity. Then we have a specific solver, which we could do one of three things, and then we definitely want to pass in an alpha, but we need to figure out how strong that L2 value should be. That's why I want to do the lassos beforehand, is to figure out, you know, what ballpark our L2 should be in. Then we have batch size, learning rate. This is going to be interesting. These are all things, less so for batch size, but for learning rate, this is going to play a big factor in how well our neural network performs. Then power T, inverse scaling rate, shuffle, which would be interesting. Next iterations tells us how long our neural network will take to build. Then random state, I always set to an integer value, and I usually use 42, because if you set it to a random state of 42, then that means it's always going to default to that same machine learning, or that same neural network pattern, and that's what we want. We want something predictable and repeatable whenever we're doing our experimentation here. Then we want tolerance. This is going to be interesting, because what if we want to find that range where our reaction or not reaction is happening? Then verbose is the default is false, but I always set it to true just because I like to know things about things. Warm start is interesting. There's early stopping is interesting. Epsilon, that could be interesting. And then we have all these attributes, which are kind of like our printouts at the end, right? Okay, so we have here MLP regressor, regressor predict, then the array, then the regressor store, and then we fit. Does it actually give us a code example? Yeah, let's do this. Advanced plotting with partial dependence. Then we have decision tree, make pipelines. Okay, cool. Hidden layer sizes. That's not exactly what I'm looking for here. So, and this is kind of what I've run into in the past, is I want to actually have control over what my model is doing a little bit more than what's happening here in sklearn. And I have used TensorFlow in the past. So let's see if we can't find anything on TensorFlow. Yeah, TensorFlow, multi-layer perceptron regression. Okay, cool. Here's an overview. This is kind of what we've talked about. We have a feature matrix and a weight and a bias. Then we have dense layer. This is more what I think I'm used to here. Load the data. Then we have our plots and our subplots. They're just kind of showing us the true labels. Then digit distribution. Cool, pre-process the data. This building, the ReLU. And then they're showing us the graph of it. That's pretty cool. Then the softmax, and they're showing us the graph of it. The dense layer. This is more what I'm interested in. Class dense layer. The dem, the activation function, which we've talked about, can be a couple of different things. Then class. Then we have, this is what I'm used to, is each layer of your NLP model, you can make a dense layer, and you can determine the size of that layer. You can determine the activation of that layer. We know that our first activation function we want to be identity. And then after that, we want to do some other different stuff maybe. And then so this is setting up, I'm assuming this is the Atom regressor that we just spoke about. This is how you would do it. Okay. Yeah. Yeah, this is more, I'm used to doing neural networks and TensorFlow. Okay, cool. And then we'll do a confusion matrix at the end for sure. Okay. So the overview here, let's see if feed-forward neural network that used to approach multi-class classification problems. Let's go back to our search here. Let's do multi-layer regression and just see what pops up. I'm used to using Keras as well. TensorFlow and Keras kind of working together, so this is not exactly what I'm looking for either. So let's look at Keras, multi-layer perceptron regression Keras, and let's see if we can get the Keras documentation. So this is someone's GitHub page. So I'm taking this with like heavy grains of salt because it's not documentation. But let's see what they do here. They added a couple of dense layers, and their dense layers are in the Fibonacci sequence kind of type stuff. And here you can see they have different activation functions. This is what I'm interested in. When I say model architecture, this is what I'm interested in figuring out is, determining how many nodes and what particular function is going to be applied to those nodes and the type of training that's going to be done. This optimizer here, that's what I'm interested in. And then the metrics, I would want to do a type of regressor like a lasso or a ridge or something. So this could be potentially a good reference GitHub page for me to look at whenever I'm trying to write my own. But that's not exactly what I'm looking for either. I'm looking for Keras. The Keras API. Let's see here. We are back in TensorFlow documentation. Keras guides, that's what I want. Give me the Keras. Oof, okay. Did TensorFlow just like eat Keras up? What's going on? Yeah, from TensorFlow, import Keras. Okay, yeah, it's a part of TensorFlow. Clean the data. Inspect, cool. Train, normalization. Normalization layer. Okay. Linear regression with one variable. We want to do multivariable. Multiple inputs. Here we go, sequential. This is what I am interested in. Two-step Keras sequential model with the first layer being a normalizer layer. Adapted to, okay, cool. So that's something that I'm going to put here. This is something that's going to require a normalization step. And we can define how that normalizer is and what it does. And then this is a deep neural network. Again, we have this normative layer, and then we have a dense layer, another dense layer, and another dense layer, and then a compile. Yeah, the activation is a ReLU function. We want to look at different activation functions. Okay, so I'm going to go ahead and, so in TensorFlow, we are in the Keras portion of TensorFlow, and we are looking at regressions. I'm going to go ahead and paste this here. And what? No, let's delete that. Let's copy that link and paste that here. And then I want to, so we've already talked a little bit about activation functions. We looked at some different examples in scikit-learn. Ultimately, I'm going to do a scikit-learn deep learning project. And then I'm going to do, you know, one using TensorFlow and Keras. And I need to figure out which activation functions are available. Then here we have hyperparameter tune. I'm trying to get to that, unless it's on a completely different page. Cool. Yeah. Okay, this is something that's pretty cool. You have some basically you can do a tuner, and at random searches, you can use the Hyperband, you can use the Bayesian optimization, or you can pull in stuff from scikit-learn. And that's pretty cool, and basically it gives you some stuff, some information. And it gives you some information about how to start training. Like here it says, you know, the first densely connected layer is 288. So you'd want to have at least that many nodes in your first layer. And then you have the learning rate optimized. So basically, you can get some information about how to best, and I think I want to do that here. Gives information about how to best tune or build out architecture for a model based on data, which I think is pretty cool. So even before you start getting, because you know, deep learning is an investment, and then you can set up different epochs, and basically what that happens is epochs are, it's solving everything in its entirety, and then each one tries to get closer. That's why you're seeing a loss and an accuracy. Here is it's comparing, and you can see that it went from 82 to 86 to 87 to 88 to 89. The idea is that your accuracy is always going up while your loss is going down. And then some additional information is you can look at the, I think this is valence or something is what the VAL stands for. But basically it's, or variant or something along that line. And then ultimately they ended here. This is what I wanted. Keras.io. Here we go. We want structured data. Classifier, classifier, classifier. Structure with wide, deep, and cross networks. Decision forest. Maybe. Classification, classification, classification. Classification, classification. Tab transformer. Is it generator? No. Graph data. Graph neural networks. No. Molecular property prediction. That's pretty cool. Code examples. Okay. Let's see. Sequential class. That's what we want. Okay, regardless of any of this, the docs to figure out stuff about activation functions and whatnot should be here somewhere. Let's go back to optimizers. Usage with compile and fit. Okay, that's not exactly what we want. Let's go to not applications. The tuner we talked about, which is pretty cool. Models API. Simple list of layers. Arbitrary model architectures. So we talked about the sequential class, but it looks like we should be using the functional API. Compile, fit, evaluate, predict. Okay. Yeah, this is really similar to what we were doing with scikit-learn. There we go, regression. So we can figure out which one of these is going to be best. Mean squared error is least. Ordinary least squares is going to be close to mean squared, or root mean squared. Absolute error percentage, logarithmic, cosine similarity, which is interesting. Losses, this is something that we can get like Poisson, and cosine similarity. Then we want to look at hinges, regression losses. Yeah. So we want to look at all of these. Okay. Now we saw the atom. We saw SGD. So one that's not in here that is in the other one is the LBFGS. But this one is different. Follow the regularized leader. That's really funny. And then we have the atom, the RMS prop. This would be very interesting. So that's kind of for neural networks. we have a lot of choices to make. Um, we got, you know, what models we want, how many layers we want. The callbacks is kind of like going back to a certain type of model, I believe. Which optimizers, which metrics, which loss function we want to use. And layers, you can do a lot of different stuff with layers. We've talked already about a normalization layer. The layer activations, this is what I'm interested in. The ReLU, it talks about, you know, how the ReLU is calculated. Then there's a sigmoid. Then there's a softmax, which we've seen a couple of times. There's a soft plus, there's a soft sine. There's the tan H, which is kind of like inverse tan. The SALU, which is a little bit different than the ReLU, but they're similar. Then there's just the ALU, which is a predecessor to those two, I believe. Then there's an exponential. Then you can create your own custom. And then advanced layers. Then there's a leaky ReLU, which I've used before. Then there's a PreLU. Okay. Softmax, ReLU, PreLU, ALU, threshold. Okay. So yeah, there's different layers. There's different activations that you can use on those layers, which is just applying a structure to a particular layer. Then there's this thing called convolution layers. You can do a 1D, which just has it change over one dimension. Then you can have it change over 2 or 3 dimensions as well. And you can have it separate out. And then there's a transpose where you just kind of like rotate it a little bit. And by rotate, I mean like you apply a certain function to the data. And you do that one time. And then you can do it 2 times or 3 times. Then there's these regulation layers. Here's our Gaussian noise, which is something that's used often in scientific type data. Our data is very noisy. It is extremely noisy data. So we might end up doing a Gaussian noise layer and then followed by a dropout layer. And we've talked about alpha regulation. That's our lasso 2. So, you know, doing a dropout layer based on that. And what that does is it kind of removes nodes. It doesn't remove data, but it removes nodes and choices, which could be interesting. We're going to end up doing a lot of regularization. And then there's the core layers. Most of it, you know, we want to have at least one activation layer. We're going to have a bunch of dense layers. And embedding or masking or lambda, those are things that we need to consider for this particular project. So I'm really glad that I found the documentation here, which is just the keras.io/API. Yeah, that's what I want to do. For the Keras documentation, because that's how I'm used to building deep layers. But we'll also do a scikit-learn, and then we'll compare and move forward whichever yields our best type of function. So I'm calling this information, this is meant to be a very quick task. It's not to make our evaluation or our opinion, it's just to get our resources that we might use later on and reference. It's to kind of give us a starting point. I know whenever you get to the modeling stage, it can be really, really exciting. So we found some information on architecture here, and I'm going to add another 4 story points. The only other thing is find external data sources. So here, discuss future model structure. We have Z remaining. I'm going to go ahead and mark this label from to do to done. I'm going to find information on different regression types. We have a list here, and I think that that's pretty cool. We have 0 remaining. I'm going to check this off as done. Remove the to-do label. And here, find information on deep learning. label, I'm going to move this from to do to done as well. And notice we were in code documentation the whole time. I'm actually going to right quick just get rid of all these tabs. Sorry if this makes life complicated. This is something else. That's pretty cool. It's related to what we're doing, but it's for a different string day. Then this find external data sets. Whenever I view the data set, external data is alongside raw interim data. And that's kind of where we're at in our Jupyter notebook, is we have our raw data and we have it written into our workspace where we can call on it. We have, you know, file names. That's our concentration. And so that's something that every third file names. And then we wanted to make a list, and I gave a couple of examples here of what I wanted the output to be like. I don't like this. This is under our written into, yeah, pull data into workspace. Okay, so we have our pull data into workspace, but we need to do a little bit of work. This create treatment plan for present data is actually going to move out of this notebook and into our scrub notebook. So I'm actually going to kind of just do that real quick and go to our find external data sources, kind of type card. I'm going to do that here. And let's get our, here, our user story with our acceptance criteria. We're going to pull that in here. So right now, to start with, let's actually run some code today instead of just talking about code and looking at what we've done in the past. We want to, right now, whenever I pull up my, is it under DF? Trials, it's under trials. Okay, so under trials, and my, let's say, 15th data set, this happens. This is my data frame for that trial. You can see the first 5 rows and the last 5 rows. That's great. That's fantastic. You can see we have 1,400 rows of data. That's pretty great. And I know that my concentration, which I think is under file names, is that right? Yeah, file names. File names 15. 25.0. That's great. I want to pool. I'm curious about something right quick here. I have another variable, so file names, this is the list file names, and it has all of my file names in it. Next page for the music. I'm using some Free Music Archive experimental genre music for my background music here. Okay, so I have my list here of my file names, and I have the adapted list of file names. And what I want to do is, I think I have a list up here called concentrations, I think. Yeah, concentrations, and these are my concentrations. So what I want to do actually is for every concentration, and for like the first 3 files, I want to add a feature called concentration. Okay. So we've done so much work about thinking about our data and framing it how we want stuff to happen. This is kind of complicated because right now our index, I like to keep my index as you know, this list of rows so that I can iterate through it if I need to later on for statistics. what needs to happen is we need to add the concentration to each data frame and not keep it separate like it is here. And we also need to add the trial. Yeah, we need to add the concentration to each data frame. We need to add the trial to each data frame. And then we need to merge all of those data frames on time. I think that's right. I think that's right. And then we want the, so we're going to have a series, so time happens. Then we have concentration happening. Ultimately, concentration is our target variable that we're trying to predict here. And everything else in this data set is to help us predict the concentration. That's the frame of mind that we need to think about this. Time between all 64 trials is the same. We know that. Actually, now we're down to 63, I think. Yeah, 63. So time is the same between all 63 trials. And so that's going to determine our row amount. However, temperature is different for each of those. We need concentration to be a variable. I'm having to keep in mind, because as a data scientist, it would be really easy to say, okay, since everything's the same on time, let's just get rid of it. But that's a really important factor. Due to how gas chromatographs work, you want a peak at a certain time, and that's how you do your what are they called? Your group, your organic chemistry groups. Is it an alcohol, an ether? Is it is a benzoyl ring? Like, what is it? Those are based on time. So different functional groups, I guess I could go with functional groups, will spike at different times. The concentration will spike at a specific time. And in fact, one transformation that I'm considering for this data is taking the average of all of the concentrations, trials of 0, which is just the, the solvent. I'm considering subtracting out that solvent data from all of the concentration data. So we're just evaluating the analyte. That's something that's commonly done. But how do I set up? Because I don't want to have 63 columns called temperature. I don't know which temperature goes with what. And ultimately, that's something that I want to get back to. But I'm having to think about, is it even important? Because this is a machine learning project, and you don't need that staunch association between data to be present for an underlying theme to be exposed. And I'm thinking about, if I merge everything on time, can I make the concentration and the trial be a part of the column name for the things that I'm merging, and how would I do that? But I think I want to start by adding concentration as a feature. So I have concentration and trial number as a feature to every data set before I try to merge anything. I think that's a good thing to start with. And then for external data, then I can pull in, and it'll be the same, it'll be similar to concentration and stuff. Well, for each concentration, it would be something a little bit different. Maybe it's better that I keep all the data frames completely separate. And I know that this is an idea that I've been struggling with since I started streaming. Honestly, it's been my biggest uh, barrier in truly starting this project is how do I structure my data in a way that makes sense, that maintains the integrity of all the relationships that I want in the data. And that's why I started streaming, was because I was avoiding this particular problem. So there you have it. Let's do file names, and then I'm just gonna work here on, let's do a split. Let's see what happens. Let's do split on the period here. Okay, and we end up with 2 values. And so if I do, I honestly should do these in different cells to show progress, but a lot of the time I just end up doing them in the same cell. Dot split, and then I want to split on the period. I want to make this a float, because this, honestly, it's not a float, but it is an integer value. And I want to take the first thing there. What do you return? You return 25. And if I do dot type, is it here? I don't, why did that happen? Come back here. Type. Okay, great. And then I want to, it's an integer, which is what I want, and it's the number 25. That's great. And then if I do this, I don't want to be an integer. This is a category, so I'm very trial 1, 2, and 3. Like, it doesn't matter what they are. And then I want to do type and then I want to do file names 15 dot split. Frankly, I'm just tired of seeing 0, 0. And so that's why I'm doing 15. It's just kind of an arbitrary number that I know is between 0 and 63. String, and it's 0. That's great. That's the first. That's exactly what I want. So I know that this splitting idea works, and it returns the values of 25 and 0, which could then be turned into a categorical. Now, I know that the regressions that we looked at today had this idea of not using categorical variables. That is for the trial types. I am planning on either merging on average or something like that. And I could do that by writing a function that says for each concentration, merge the categories 0, 1, 2, and do it on average. That is a thing that can happen in the future. And it's also why I'm okay with leaving this raw data, kind of like this trials and this file names kind of associated like they are, is in case I need to do something like that in the future. I have a couple of options for how I could do that. So I want to keep this category for now, and then I can also do some things statistically to figure out later on based on this naming convention. Like I can group on concentration and then drop the trial, but you know, for my human brain, I want the concentration in there until it doesn't have to be. Not the concentration, the trial number. Okay. Then if I were to, let's set up something here. I have trials as my DF. Let's do I have anything under conx? No, that's great. Let's use conx, short for concentrations. Equals trials. And now I can look at conx 15 and see here that I have this row. Then I could say conx 15. In this data frame, I want there to be a conx 15. Then I want to do concentrate I want a label, a category, or a column label of concentration, and that concentration was in microliters, or micrograms per liter, and I want this to be in this kind of type notation. And I want to set this equal to, there it is, int, file names, 15, dot split, and I want to do this on the period, and I want to take the first value. Now, let's see what conx 15 looks like after we do that. File names is not defined. Oh, files names, that's funny. Okay. Concentration 25. Let's do conx 15, and let's look at concentration micrograms per liter. Dot unique, and it's 25 the whole way down. That's perfect. And then let's do conx 15. We want a new column called trial, and this is going to equal our file names 15 dot split. On the period, we want the second value in that list, and then let's do conx 15 trial dot unique. Okay. So here we have our integer value, and then we have an object value. That's going to cause some issues whenever we go into scrubbing, but I think it's okay for now. And then we want to do both of these same things, you know, at the same time. So we have our conx equals trials, and then let's say for I in, let's do for I in, let's do conx, we want to say I concentration, okay, for I in range of 0 to the length of conx. And the reason why I say UG, you'll see in a second, we need to do conx I concentration in micrograms per liter, and we want that to equal to the int file names. It's so that we can get that same I variable here in this other different list. Dot split, we want to do that on the period, and we want to take the first value and we want to set it to that integer. And then we want to, as a test, we want to print conx I concentration in micrograms per liter. Dot unique. Then we want to do conx I, and we want to print trial dot unique. Okay, conx I, we want the trial to equal file names I split on a period, that second value, and let's see what happens. Okay, we have 0, 1, 2, 0, 1, 2, that's great. Then we have 10, then we have 15, we have all of those, then we have 1, and then we skip to 3, which doesn't matter, but it's good for scientific recording purposes. Here. Okay, that's great. So now we have this list where, and here, I guess you could say conx, and let's do a number that's different. I don't want to import random. Okay, let's do, this is where I would say if I had any viewers right now, which, cool, then I would say, hey, chat, pick a number. I'm gonna do, let's do 70, not 75, there's only 63. So let's do 42, because I said I'd choose that all the time earlier. Yeah, let's just look at that data frame. And here we have our concentration, and we have our trial number. And let's do dot sample, let's look at 5 rows, and then let's also look at a different number. Let's do 43 to see if our trial number goes up by 1. And then we'll just look at 5 numbers. Yeah, and our trial number goes up by 1. That's pretty cool. And we can see too that at 1255 and 124 that we're spiking pretty high. We're definitely outside of temperature, so that's pretty cool. So this, I'm gonna go ahead and hit save. And I'm gonna bring up my status here, and I'm gonna hit get status. And I can see that I have made a modification. Then I'm gonna do get add. Get status. Get commit, and we have added concentration and trial number to data frames. So that is something that we have done so far. We have our concentration and we have our trial number. And what might be interesting is I think I might create something that's like merge on merge data frames on concentration, and then I might say, you know, temperature plus trial as a new column. And then work from there. I think that that is going to be a little bit better of a setup. I think this is a pretty good setup here. Something that I need to do is I need to set up an export to interim folder for next Jupyter notebook for scrubbing. I think that this is a really good stopping point for today. We've added our concentration, we've added our trial. I think that we should keep all of the data frames separate until after scrubbing, because we might encounter some issues where in some of the data frames we have missing numbers or nans or something from file corruption. And that's something that I haven't been able to evaluate yet because it's a lot of information and it's a lot of numbers on a page. So I want to export these concentration labeled data frames into a series of CSV files so that we can import them similarly to how we did here, where we set up, file names. And the file names I want to, I'm probably going to name them really similarly so that we can just set it up all the same way to import in our next section. But we've gone from this like XML to something that's a little bit more usable. Oh yeah, I forgot to mention, or like here, we need to, also before we do that, we need to pull the start time for column 1 and column 2. And we need to redo basically all of this with those start times. Okay, so before we do that, we need to import start times from OG raw data before moving on, because we need to export that with us whenever we go into scrubbing. Okay, I'm gonna save, and I'm going to go back to my Git bash terminal here. Git status, you'll see that I've made more changes. Let's do git add. We want to stage this particular notebook for commit, and it has been staged. We've moved from red to green. Then git commit, and I'm gonna put message, add note for next steps before exporting data for next notebook. Git status, and I'm going to go ahead and push up all of these commits so that they are on the master branch. Now after we're done with this import, I think I'm going to set up a branch that's called scrub, and everything that I do on the scrub branch, I want to be part of that scrubbing process. If I do anything on the explore side of things, more into statistics, then I want to kind of open up a new branch called explore and go from there and practice merging branches onto a master or main branch. Anyway, thank you for watching today. If you have any questions about anything that I discussed today or anything like that, just feel free to post them in the chat. Again, the way that I searched for the information was I include the word documentation to make sure that I'm looking at the original documentation and not necessarily somebody's blog post about this content, because I want to get it from there so that I can pull out my list of terms to go research later on, like normalization and that kind of type stuff, and this LBF or LBFGS type modeling for deep learning. So yeah, if you have any questions, please feel free. You can see that we're starting to move more into thinking about our data as it will turn into a model. And I'm excited to continue that process with you guys next time. Anyway, thanks. And I'm going to end the stream here. All right. Bye.